Consider a vector field that's given by f of x, y, z equals x plus y I, y minus zj, and z squared k. And the curve through the vector field, which is parameterized by r of t equals t squared I plus t cubed j plus t squared k, t goes from 0 to 1. Now, I want to evaluate the line integral of the curve through the vector field. Now, I know from r of t, I know from here that x equals t squared, y equals t cubed, and z equals t squared. And I also have here, or I can get from this, that f of cx, y, z I can write as f of r of t, which is going to be, let's see here, x plus y, so that's going to be t squared plus t cubed. I'm going to write this as straight as a vector. Y minus z, that's going to be t cubed minus t squared. And z squared is t squared squared, which is t to the fourth. I also know that, actually I shouldn't say implies, but I know from here, if this is r prime, then I know that, I'm sorry, if this is r of t, then I know r prime of t is going to be 2t, I'm going to keep writing these as vectors, 3t squared, 2t. So now I have everything that I need to go ahead and evaluate this line integral. So this line integral over the curve is going to be f dot dr, which equals the integral from a to b of f of r of t dot r prime of t dt, which is going to equal the integral, t goes from 0 to 1, f is now, let's see, t squared plus t cubed, and t cubed minus t squared, t to the fourth, dot 2t, 3t squared, 2t dt. So I take this dot product, I'll get the integral from 0 to 1 of, let's see, I'll have 2t cubed plus 2t to the fourth plus 3t to the fifth minus 3t to the fourth plus 2t to the fifth dt, which if I collect some like terms, I'll get the integral from 0 to 1 of 5t to the fifth minus t to the fourth plus 2t cubed dt, which is equal to, when you work this out, 17/15. So if this vector field is some type of force field, this is a measurement of the amount of work that was done by the force field when I'm moving along this curve from time t equals 0 to t equals 1. So let's go ahead and take a real quick look here at Maple. And what I've done is I set up the space curve and the vector field, and we're going to ignore this one for right now. We're just going to take a look at A and B. And this is what I get. This is my vector field, and this is the path that I traveled. Let me make this a little bit bigger. And you can see the vector field's predominantly pointing like in this direction. You know, obviously it's not straight. There's different things going on there. You can see that. But in general, I'm kind of moving with the force field or with the vector field. Not always, not everywhere. As I spin this around, I can tell, you know, at some points I'm moving relatively nicely with it. Other points kind of against it. But in general, I'm moving with it. So this positive answer of, what was it, 17 over 15, it makes sense that it was in fact positive. But what happens if I simply travel from this point to this point, only I make a direct path? Then what happens? Well, I'm glad you asked. When t equals 0, r of t is at 0. When t equals 1, r of t is at 1. So I'm going from the point 0, 0, 0 to the point 1, 1, 1. So I want to parameterize this line segment because that's what I'm talking about doing. It's a straight line. So this would be 1 minus t plus t times this. Well, this is all zeros. So this is just simply equal to the vector t, t, t. So let's go back to Maple now. And I'm going to add to it that last space curve, which is this at t, t, t. And you can see this is now the path that I'm talking about. So I'm going to follow this direct path from 0 to 1, or 0, 0, 0 to 1, 1, 1, rather than this curved path. Now, is that going to make a difference in regards to the amount of work that's being done by this force field? Well, this is now my new r of t. That would then imply that r prime of t equals 1, 1, 1. So what I'm looking for is the integral from 0 to 1 of f of r of t, which is still going to be t squared plus t cubed minus t squared t to the fourth dot 1, 1, 1 dt, which is just going to be equal to the integral from 0 to 1 of t squared plus t cubed minus, whoops, this is supposed to be cubed, minus t squared plus t to the fourth dt. And this is supposed to be cubed. Didn't write those quite right. So the t squares go away, and I'm going to end up with 0 to 1. What do I have here? I have a t to the fourth plus 2t cubed dt, which is going to give me t to the fifth over 5 plus 2t to the fourth over 4. I'm sorry, that's canceled to be 2. So I will rewrite that as t to the fifth over 5 plus t to the fourth over 2, evaluated from 0 to 1, which is a fifth plus a half, which is 7/10. These two are not equal. So in this case, the path was in fact influential, or it did have an effect on the amount of work done, if we're thinking of this as a force field, by that vector field. Now notice that 7/10, that's 0.7, that's less than 1. 17/15, that's 1 and 2/15, that's slightly bigger than 1. So if we're thinking in terms of the extent that our space curve is moving with the vector field, then that curve field appears to be moving more in the same direction than that straight line. Which, when I look at this, at first I think, what are you talking about? But when I start twisting this different angles, I can see that the straight line is near orthogonal to quite a few of these vectors. So it really does not follow the flow very well. I mean, you can spin this around, you know, quite a bit here, fiddle with it, and it does suddenly kind of make sense that this blue line, by looking at this, does in general seem to follow the flow a little bit better than that black line. Now, as it turns out, in this case, these two line integrals resulted in different values. But that's not always the case. There are situations where we are, in fact, path independent. It doesn't matter which route you take to get from point A to point B. The fact that you start at one point and you end at another, the path that you take to get to those 2 points or from one point to the other actually becomes irrelevant, and the line integral is the same value. We'll take a look at some examples of those and get quite a bit deeper into that idea.